So section 4.3 is Newton's second and third laws. Our objective is going to be to describe the acceleration of an object in terms of its mass and net external force, which you've already noticed from the lab that we worked on, and to identify and explain action-reaction pairs. So let's take a look at data from a spring scale and motion detector. Imagine we have an object and there's some sort of a hook on the end of the object. Into the hook we hook in what's called a spring scale with a reader with an output, and then we apply a force this way. So we're able to measure how much force it is, and at the same time the motion detector can measure the acceleration. So this is the values we have. What we're noticing is that when the acceleration is 2 and the net force is 6, what factor is that really we're seeing? Well, we're seeing a factor of 3 there. When the acceleration is 5, we notice that the net force is 15, which also increases by a factor of 3. And you'll notice that all of these increase by a factor of 3, which tells me that I can take my acceleration and multiply it by some factor to always get the net force. So I could take the acceleration and multiply it by some unknown factor to give me the net force. Well, it's interesting to think about this. We don't necessarily know what that factor is, but it's some number, some quantity. So we can give it some random name or any given variable. Call it K for now, or call it alpha, or call it beta. It doesn't matter. I'll call it, let's say, alpha for now. And what we're going to notice is there's got to be some quantity that relates these two, these force and acceleration. And the easiest way to look at it actually is to look at the units. So for units, the units of acceleration are meters per second squared. These units are unknown, and units of force are kilogram meters per second squared. So just by inspection, you can see what's missing. Clearly, this has to be kilograms. So we have kilogram meters per second squared on both sides. So if it's kilograms, what's measured in kilograms? Well, masses. So this unknown or missing factor is mass. And this is going to lead us into Newton's second law. Newton's second law tells us that an object's acceleration is directly proportional. Acceleration is directly proportional to the net external force. So that's in the numerator. It's directly related, but it's inversely proportional to the mass, which means that's in the denominator. And solving this, like we did multiplying by mass, gives us Newton's second law in the simplest term that most people see it, F equals ma. Please remember that this is a vector law, so this applies in direction. So we could say Fx equals the mass times the acceleration in the x, and Fy equals the mass times the acceleration in the y. And we're going to have to split up our directions to solve the problems at hand. Let's take a look at example 1 now. Example 1 tells us space shuttle astronauts experience accelerations of about 35 meters per second squared, almost 4 g's during takeoff, almost 4 times that of gravity. What force does a 75 kilogram astronaut experience during this acceleration? So let's list our givens. Acceleration is 35 meters per second squared. Okay, since it's liftoff, it's moving vertically, we can call this AY, but it doesn't really matter here, it doesn't ask. We also know that the mass of the astronaut is 75 kilograms. So if I want to find the force that is felt, I simply have to look at F net in the y direction and say, well, that's m times AY. Well, F net is simply going to be 75 kilograms times 35 meters per second squared. It's going to give me F in the y direction. I can drop the net if we keep realizing that it's going to be there every time. That'll give me a force in the y direction experienced by the astronaut of 2,625 newtons. And notice the symbol newtons. Well, where does newtons come from? Kilogram meters per second squared. This is the force that the astronaut is actually feeling. Almost 4 times his actual weight is being felt, 4 g's. Let's take a look at example 2. A bowling ball initially at rest is dropped from the top of an 11-meter building. It hits the ground a second and a half later. Find the mass of the ball if the net external force is negative 74 newtons. Okay, negative 74 newtons. Well, for this problem, we know right away already. We've got our acceleration. Why do we have an acceleration? Well, it's dropped and it's moving vertically. What's the acceleration always going to be? The acceleration is going to be negative 9.81. A lot of people try to solve for the acceleration first, and then they use the acceleration. But you don't have to solve for it. It's negative 9.81 meters per second squared. The other information is extraneous. The height of the building, the time period. Sure, it's given to us, but we don't really need it. We have the acceleration. We also have the net external force. That's going to be negative 74 newtons. This happens to be in the y direction. Let's say Fy equals MAY. Solve for mass. Mass is just Fy over AY. So our mass in this problem is going to be a number of negative 74 newtons over negative 9.81 meters per second squared, giving us a mass of 7.5 kilograms. Again, you could have solved for acceleration, but you're going to get negative 9.81. So that information about the height of the building and the time period, sure, it's useful, but in this problem, it's not. So example 3 says, an object accelerates from a velocity of 6 meters per second to 15 meters per second in 10 seconds. So right away, we know we have acceleration, because it's change in velocity. And we're given a time period, so we can definitely calculate acceleration. If the object's mass is 25 kilograms, what net external force must be applied to accelerate this object? So let's find that acceleration right away. Our givens are our initial velocity, final velocity, time period, and mass. To find acceleration, remember we're looking at the change in velocity over time. Okay, so the change in velocities is going to be 15 minus 6 all over 10, okay, which is just going to be 9 over 10, so the acceleration is 0.9 meters per second squared. That's the acceleration in this problem. Now, that piece is needed this time. In the last problem, we didn't have to calculate acceleration with that extraneous information, but now we did. And we know that F equals ma is our law, so let's go ahead and plug in. M is 25 kilograms, A is 0.9 meters per second squared, giving us a force of 22.5 kilogram meters per second squared, or just newtons. Newton's third law tells us that for each action, there is an equal and opposite reaction. There's an equal and opposite reaction. Now, it's very interesting to look at this though, because we think right away, oh, it's got to have an equal and opposite reaction. But the problem is this. If the object can't withstand a certain force, it will fail and it will break, and you won't have that reaction. So if you hit a table with a force of 5 newtons, the table will hit back at you at 5 newtons. But if you hit it hard enough, eventually it would break, or your bone would break, or something would break, and it wouldn't be equal and opposite eventually. So we have to consider the fact that it doesn't always result in a state of equilibrium. So let's take a look at an example of what I'm talking about. Imagine a force of a hammer on a nail. If you hit a hammer and you hit the nail, you're hitting it, let's say, against the wall. And the wall hits back on the nail. But for that nail to actually go into the wall, or into the wood in this case, whatever it is, that force that the nail is pushing with onto the wall has to exceed it, clearly. So really this happens because they act on different objects. Okay, so in this case, if you look at this, you're going to see that the forces are not balanced here. They're not the same. So because there's a net force of the hammer on the nail that exceeds the force of the wood on the nail, well, here's your wood right here. Here's your hammer on this end. And the hammer hits the nail to the left. So the hammer hits the nail, it drives it to the left, the wood pushes back to the right, but the wood doesn't push backward enough, so that nail goes into the wood. Because there's an unbalanced force here, we have F net, which means we have acceleration. Because this exists, it's not zero, this must be some value also. So that nail is going to accelerate. Where is it going to go? Right into the wood. Another way to think about this is to think about field forces. They also come in pairs. Even though we might say that the earth pulls down on us to the surface, we're also pulling back on the earth. So for this, what I'm saying is the following. Imagine you're on the earth, and a person decides to jump in the air. Well, as they're falling down, the Earth is pulling them down, so the Earth is making them accelerate toward the Earth, while the person is also accelerating the Earth toward it. But think about the mass of the Earth. The mass of the Earth is very large. So even though these forces are equal, watch, take a look. That's for the Earth, and here's for the person. The forces are clearly the same, but the mass of the Earth is some number, let's say like, it does not matter, let's say 1,000,000, and I'm not even going to put units. Well, if that's 1,000,000, then the mass of a person is like 1. So for these forces to be the same, this acceleration has to be very large for this to be the same force as the force that we would get on this side of the equation over here. This acceleration has to be very small. So let's say this acceleration happens to be 1, well this acceleration happens to be 1,000,000 then. Again, if the mass of the object is much smaller, even though the forces acting against each other, or pulling toward each other, gravity in this case, are the same, the accelerations are so much different. So you don't even see the Earth accelerating. It is pretty much negligible. For homework in this section, I want you to look at 2 parts, from 138 and from 140.